Good morning, gang. Welcome back to college algebra. Today we're going to talk more about linear functions. We're going to talk about some modeling problems. And we're even going to talk a little bit about something called linear regression. I'm still working with Santa Fe IT to try and get my graphing calculator emulator to run from this computer here at home. And unfortunately, they're not answering my calls this morning. So when it gets to that portion, I'll have to make a decision whether or not we're going to try and use the calculator through the document camera, which doesn't really work very well, or postpone that until next week. If we end up postponing that until next week, of course, I will extend the associated homework assignment. But I'm pretty sure we can get through this without too much hassle, so let's dive in. Let's see. Make sure we have this up over here. Okay. All right. So we talked last time about linear functions and average rates of change. We talked a little bit about parallel and perpendicular lines. I'd like to do one more problem similar to those. And then move on to some material from the next homework. So a little more lines and linear functions. We're going to talk about absolute value functions. I should add equations here. And then if there's time, we're going to get to this regression stuff, which is really a calculator thing. And again, that's the issue for which I'm trying to get an emulator to work, but still haven't had success. So let's do it. Last time we talked about parallel and perpendicular lines, linear functions, and average rates of change, which are intimately connected to lines. I want to look a little bit at some linear equations and some linear functions that arise as models. And I figured the way you guys would most appreciate that is if I took some of those problems from the homework. So let's do that. We can look at one or two problems from here. Are there any particular homework problems? So I'm going to go through, we're going to do a few from homework 4 and a few from homework 5, a few from homework 6. Is there anything in particular from homework 4 that you guys would like to see? Remember, you can hold spacebar to talk, or you can type into the chat. If there are no requested problems, I'm going to grab one of these guys. So we'll start off nice and gentle. Let's find the x and y intercepts for this fella. 4x minus 5y equals negative 20. So this is coming from homework 4, and it's number 15. Yeah, sure, Kendra. I'll come back to problem 4 in just a second. We'll use that for our second example. Who can help me get started on this one? How do I find the x and y intercepts for this line, 4x minus 5y equals 20? What are x and y intercepts algebraically? How do we find them?
It's where the value is equal to like 0.
Yeah, each one of those is a place where one of the variables is equal to 0. Along the x-axis here, the y values are all 0. And along the y-axis here, the x values are all 0. So I'm just going to draw some line here. It's not necessarily the line we're looking at over there, but at the x-intercept here, the y values are 0. And at the y-intercept over here, the x value is 0. So that means if you want to find an x-intercept, you need to set y equal to 0 and solve for x. If you want to find a y-intercept, you need to set x equal to 0 and solve for y. So finding the x-intercept, we set y equal to 0 and solve for x. And if I set y equal to 0 in this expression, then I'll get 4x minus 5 times 0 equals negative 20. 5 times 0, that's definitely 0. So this just says 4x equals negative 20, right? 4x minus 0 is just 4x. And then I can divide both sides by 4. And negative 20 over 4, well, 20 is 4 times 5. So if you divide 20 by 4, you get 5. So this is negative 5. So that means my x-intercept, and you always want to report these as ordered pairs, the x-intercept is the point negative 5 comma 0. So again, this line is not necessarily this line, right? I just drew a random line here. If I want to find the y-intercept, here I'll have to set x equal to 0 and solve for y. Right? Because y-intercepts all along this y-axis here, the x values are 0. Plugging in x equals 0 to that equation gives me 4 times 0 minus 5 times y equals negative 20. And 4 times 0 is 0. 0 minus 5y, that's the same as just minus 5y. So this is minus 5y equals negative 20. And then just like in the previous guy here, if I want to solve for the variable, I have to divide both sides by this number. So if I want to get y alone, I divide both sides by negative 5. Negative 20 divided by negative 5 is positive 4. So all this work tells me that the y-intercept is the point x is 0, so it'll be 0 comma 4. Any questions on finding x and y-intercepts for a linear function?
In the homework, is this how we would write it out too?
Yep, and
Okay, cool.
so in the homework they you'll be working on your own paper obviously, and then in the my math lab they'll ask you to enter an ordered pair like this. So if we come back and look at this particular problem, they say type the answer as an ordered pair. So just make sure you type it as like parentheses, one number comma the other number, right? X comma.
Okay, cool. Thank you.
Yeah, of course. Now a neat fact, these rules are always true. This isn't just true for lines or linear functions. If you want to find x-intercepts for any function in the world, the way you always do it is by plugging in 0 for y and trying to solve for x. And the other way around is true as well. Anytime you want to find y-intercepts, you always plug in x equals 0 and solve for y. So while we're learning this in the context of a linear function, this extends to functions in general. Even relations in general, not just functions, any sort of algebraic relation that you can graph. This is how you find x-intercepts. Set y equal to 0, solve for x. And this is how you find x-intercepts. set x equal to 0. I'm sorry, how you find y-intercept, set x equal to 0 and solve for y. So this business always works. And the logic is just what we said here. The y-axis is all the points whose x value is 0. So if you want to find the y-intercept, you need to find the point on the graph of your relation who has x value 0. So to find that, you would set x equal to 0 and then solve for y. It's good stuff. Kendra wanted to try number 4, and I invite you guys to go ahead and request any other problems that you want. I'm happy to spend a meaningful amount of today on examples before we talk about absolute value stuff. So this is actually a problem we've done in class. I don't mind running through it again. We can do it quickly. But if you want to see this done a little bit more slowly, I invite you to go back to our previous lecture. So we want to find, this is homework 4, number 4, find the line, find the equation of the line containing, I think usually I say this as passing through the points -1, -2, and -4, -9. It's never a bad idea to draw the picture. All right, so we can take a second to sketch this picture. You notice that the x values and y values, they're all negative, and the y values go quite a bit down. So I'll give myself a lot of space like this when I draw my axes. Let me call this here -1. And call this -2. Give myself even more space. We'll exaggerate this a little bit. We'll call that -9, and we'll call this -4. So -4, -9 is way down here. -1, -2 is right here. And it's hard to say based on this picture exactly what is going to be my y-intercept. Right, but here's a rough picture of my line. Does anybody remember how we do this? It was a good little refresher, right? Because this is something we've done in class previously. Definitely an important skill.
We have to find the slope.
Very good, right? We need two things to find the equation of any line. We need the slope, and we need a point on the line. So strategically, in my mind, if I'm planning ahead, I'm thinking, okay, I'm going to use the point slope formula, which is y minus y0 equals m times x minus x0. So I need 1, a point on the line, and 2, the slope of the line. Right, those are the two things I need. I actually have 2 points on the line. That's great. So let me come in here and label this as x0 and y0. I'll label this as x1 and y1. And you could, again, switch these. This could be x1, y1. This could be x0, y0, as long as the zeros go with the zeros and the ones go with the ones. Now I can calculate my slope. Y1 minus y0 over x1 minus x0, right? Rise, or a change in y values, over run, a change in x values. So it's going to be y1 minus y0, -9 minus -2, all divided by -4 minus -1. Now upstairs, -9 minus -2 is -9 plus 2. And similarly downstairs, that's -4 plus 1. So we get -7 divided by -3, or positive 7/3. And that's really all the calculation work I need to do, because now I can use this formula with 7/3 plugged in for m, and these numbers plugged in for x0 and y0. Therefore, these three dots arranged like this mean therefore the equation of our line is y minus y0. Okay, y0 is -2, so y minus -2 equals m, which is 7/3, times x minus x0, which is x minus -1. So getting used to using this point slope formula is a bit of a step, and it's something that we will need for this class. We'll need it again and again, so please don't hesitate. Mark asked a good problem in chat. I'll come to that in just a second, Mark, okay? So let me clean this up just a tiny bit. This is y plus 2 equals 7/3 times x plus 1. And if we wanted to put this into y equals mx plus b, I won't always do this, but we can. This is the same as y plus 2 equals 7/3 x plus 7/3. It's healthy practice with fractions to see what we get when we subtract this 2 over. This would be y equals 7/3 x plus 7/3 minus 2. So I need to combine these two fellows. So I have to write 2 as a fraction whose denominator is 3 in order to get a common denominator with this. So I can write 2 as 6/3. So 7/3 minus 2 is the same as 7/3 minus 6/3, which is positive 1/3. So this is y equals 7/3 x plus 1/3. If you wanted it in that slope intercept form. Okay. Mark asked an interesting question. Maybe this will be the last little example problem I do. I'm not sure from which homework problem that comes. Mark, could you tell me what problem number that is and from which homework number, just so I can let the rest of the class know? Sure. While you're checking, I'll go ahead and introduce the idea of the problem to the class and your question. So there are some problems in the homework that ask you to solve equations graphically. So I could ask you to solve, Mark's example here was 2x plus 5 equals 3x minus 6 graphically. And one way to approach this, one option, is to graph the two lines, y equals 2x plus 5, call that y1, and y2, we can call this, oh, now forget the 1s and 2s, we'll just call them both y. Y equals 3x minus 6. We can graph both of these. 2x plus 5, of course, is a line with, call this 5 up here. slope 2 and y-intercept 5, he'll look something like this. And 3x minus 6, a slightly steeper slope. Slope 3, so my pen isn't really cooperating. Steeper slope there, and y-intercept -6. So if you have perfect graphs of these lines, then you can figure out the x value that solves this equation by finding the x value of this intersection point. Now, I would hope that on such a problem, where they ask you to solve it graphically, they would give you the graph. Did you find that problem number there, Mark? Okay. Well, Mark's question was instead, so here, this x value, this x value here would be the solution to the equation. Solution to the equation 2x plus 5 equals 3x minus 6. So the x value where these two lines intersect would be the solution to this equation. But Mark's question was, isn't it just easier to solve this equation algebraically? And the answer there is yes. So if they gave me a perfect graph from which I could easily read off the solution, then that will be fastest. But if they do not give you a perfect graph from which you can easily read off the solution, then by all means, just use algebra. And since we haven't done something like this together yet, even though I'm sure you've all done it many, many times, I just want to run through the procedure once. So how do you solve a linear equation in a single variable? By hand, algebraically. What would be my first step if I wanted to solve this just using algebra?
Get all the x values on one side and then all the non-x values on the other side.
Yeah, Logan's comment there that we should get all the x's on one side and all the things without x's on the other side. Perfect. I have a 2x over here and I have a 3x over here. So if I subtract 2x from both sides, then on the left-hand side, I'll just have a 5. And on the right-hand side, I'd have 3x minus 6 minus 2x. Yeah, I trust that the numbers probably are different, but that's okay. These are randomly generated anyway, so everybody will have different numbers. All right, now the two terms that have an x in them are on the right-hand side. I'd like to get this 6 over to the other side because he doesn't have an x in him. So my goal is to get all the x's on one side and all the non-x's on the other side. The only sort of non-x I have on the right-hand side is this -6. So I can add 6 to both sides. Now 5 plus 6, that's 11. So I get 11 equals 3x minus 2x. And then over here, like 3 apples minus 2 apples is 1 apple. These are like terms. I can subtract them because they both have this x attached. So this is the same as just saying 11 equals 1x. 3x minus 2x is 1x. So kind of here's your first step, here's your second step, and here's your third step, which gives you your solution. So yeah, I would agree that if I wasn't given a graph, if I was just given these two and told to find where they intersect, or if I was just given this equation and told to solve it, I would proceed exactly like this using the algebra. But if I was given the graph, let me pretend for a second that we did have a nice graph. We'll come over to Desmos here. I don't want to waste class time hunting through the homework for that particular problem. So let's y equals 2x plus 5, y equals 3x minus 6. And then I'm going to have to reset my axes here because I was doing something funny for my calculus classes. Here we go. So if I was given a really nice graph from which I could see the intersection point clearly, the x value of that intersection point is my solution. And you see the picture looks just like the one we drew. But from our picture, it's not so easy to read off the x value of that intersection point. It depends on the quality of the graph you have to work with. Any questions on any of these examples we've done so far? Okay, Kendra would like to see number 20. Is that from the same homework set, number 4 here? So that's this fellow. We want to know, is this a linear equation or not? After this, we're going to talk about absolute values a little bit. I'll write it down. So homework 4, number, what is this, 20, is the equation 3 square roots of x plus 1 equals 11 linear. So to answer this, I'd like to answer a more broad question. How can you tell? If an equation, or more generally, a function, is linear? Well, linear equations and functions can be identified a few ways. One, the graph will be a straight line. So here I don't have a function, right? I have this equation. I don't have a graph to talk about. So I can't use this. 2. The independent variable which is the input variable, usually x, or sometimes t, sometimes it'll be other things, must occur only to the power of 1 and never in the denominator of a fraction. Remember, having a variable downstairs is like having it to a negative power. Or under a radical. Because remember, a radical, like a square root, is the same as a 1/2 power. So if you have the graph of the relation or the function, whatever it is you're talking about, if that graph is a straight line, then yeah, that is a linear function or relation or whatever. If you don't have the graph, if you just have to look algebraically, the thing to look for is that the variable in question occurs only ever to the power of 1, meaning there is no x squared or x cubed. There is no x to the 1/2 or x to the 3/4. There's no x to the -1, or variables downstairs, like 1/x or 1/x plus 5. Anything like that would be nonlinear. So the following are linear. 2x minus 3y equals 7, or y minus 4 equals 1/2 times x plus the square root of 3, or f of x equals 1/10 x minus pi. These are all linear. And the trick is to look for the variable x. Does the variable x ever show up downstairs, or under a radical, or with any weird powers, any powers besides 1? No. In all of these, the variable x shows up only in the numerator of any fractions. Here, we don't even see it in any fractions. Shows up only ever with the power of 1, and is never underneath a radical or anything like that. Well, the following things here are nonlinear. Something like y equals 1/x, or f of x equals the square root of x plus 2, or x squared plus y squared equals 7. These would all be nonlinear because, for example, here you have you have an x value downstairs, right? You have the variable x showing up downstairs in the bottom of a fraction. Here you have the variable x showing up underneath a radical, which is not okay. Definitely breaks this rule, right? Never under a radical. And here you have the x variable showing up to the power of 2. So this certainly cannot be a linear relation. So these are what linear things look like. These are what nonlinear things look like. There's way more nonlinear things out there than there are linear things. And you have to be careful. Sometimes that they can be a little bit tricky. Like you'll notice here, there is a square root, there is a radical, but the variable x is not underneath that radical. So this is still linear, even though there's this radical. Or here, there's a fraction associated with the variable x, but since the x doesn't show up downstairs in the fraction, this is still linear also. And when in doubt, if possible, you can graph the object in question and ask, okay, is this graph a straight line? So having done all of this, let's come back to the question we were trying to answer. I'll zoom out a little bit. We want to know, is this a linear equation? Who can help me out? Is this or is this not linear? Yeah, beautiful, Kendra. It's not linear. Why is this not linear? Perfect. Yep, you nailed it. Because the x is under a radical, right? This is the same as having x to the 1/2. And that certainly is not a power of 1. So we cannot call this a linear equation. Okay. So as you run into other problems in the homework that you would like to discuss in detail, please don't hesitate to bring them up in class. I'm happy to do what we just did here and spend a little bit of class time each day solving problems that you guys want to solve from the homework. There's a lot of stuff in there, and a lot of it is review from previous classes. So it's a little tough for me to know exactly how much time we need to spend on some of these sort of review topics. I know people come to 1105 from a bunch of different backgrounds. When I took college algebra the first time, the last math class I'd had was in 8th grade. I didn't remember shit, but I know that there are also people in my college algebra class who'd taken pre-calculus in high school just the year before, and they knew everything, and it was very intimidating. So we come to this class from a bunch of different backgrounds, and any question you want to see is worth talking about. Before we go, I want to talk a little bit about absolute value functions and absolute value equations. All right, and this is stuff that is related to homework 5. I'm sorry, homework 6. Yeah, homework 6 here. We'll also talk about absolute value inequalities. The place to begin here is let's look at the graph. Consider the function f of x equals the absolute value of x. If I want to draw a graph, to graph this function, we can make a table. All right, and to graph any function, you can always try making a table. It won't always give you the full perfect picture, but it'll often give you something to get started with. So to do this, we make a table of values. On the left are inputs, and on the right are outputs. And for my inputs, I'm going to use like -2, -1, 0, 1, and 2, just to get started. Those are easy numbers to work with. You could use whatever numbers you wanted, but these are easy ones to get started with. F of -2 is, well, to find f of anything, you feed it in here, which means you plug it in for x in this expression, and we see what we get. So that would be the absolute value of -2. And the absolute value of -2, that's just 2. All right, remember what the absolute value function does. If the thing you feed it is positive, it leaves that thing alone. If the thing you feed it is negative, it corrects that and makes it positive. So the absolute value of -2 is just 2. The absolute value bars here, they just strip away that negative. F of -1, that would be the absolute value of -1, which is +1. F of 0 would be the absolute value of 0, and that is 0. F of 1 is the absolute value of 1, which is 1. And f of 2 is the absolute value of 2, which is 2. So here's what my table looks like. Some people don't write this part. I'm writing it just to help you see the function notation, just to help you get a little bit used to what this notation means. That's one of the things we need to incorporate in our thinking in this class, is function notation. But this tells me that the ordered pair -2, 2 is on the graph. Mark this as -1. This is -2. This is 1. Mark this as 2. And here on my y values, mark these as 1 and 2. So the first row of this table tells me that the ordered pair -2, 2 is on the graph. When x is -2, the y value, f of -2, is +2. This line of my table tells me that the ordered pair -1, 1 is on my graph. So that ordered pair lives right here. This row of my table tells me 0, 0 is on my graph. 0, 0 is right there. This line tells me that 1, 1 is on my graph. And this line tells me that 2, 2, right? 2, 2 is on my graph. So everywhere over here, my graph looks like this. And everywhere over here, my graph looks like this. Big fat point here. So this is what the graph of the absolute value function looks like. Just good old-fashioned absolute value of x. It's this V-shaped graph with a point like a pointy end down here at the origin. This, of course, is my x-axis. And there are a lot of ways we can modify this graph. We can shift it left and right. We can stretch it vertically. We can compress it vertically. We can move it all around. Anytime you need to graph any function, I'll say this again, especially in this homework, when you're looking here in homework 6 on absolute values, try making a table. If you're having a hard time sorting it out, try making a table. The table is your friend. Let's take an example problem from that section. From that homework. So they're asking some questions about domains and ranges, increasing and decreasing. We haven't talked much about increasing and decreasing, but let's do it. So looking at this graph, what is the domain? And what is the range? We remember the smooshing game from the first week? We talk about smooshing everything onto the x-axis to find the domain, smooshing everything onto the y-axis to find the range. These arrows like this indicate that the graph goes on following this pattern forever and ever and ever. Yeah, so Mark said that the domain is all real numbers, all of R. And that's correct, because since these graphs continue on like this forever and ever, if you were to smoosh the whole thing down onto the x-axis, everybody gets hit. Another way to say this is there isn't any number that you can't plug in here, right? You can plug any number you want in here. This function is happy to eat as an input all real numbers. So my domain is negative infinity to infinity. Or you could write this as all real numbers. If you're feeling very fancy, there is a special notation for this. It's called a Blackboard bold R. And it's kind of an R with an extra leg like that. What about my range? So most of the time you're going to work with interval notation, right? This is how I prefer your answers, just to be clear. Can anybody help me finding the range of this function? What is the set of all outputs? Yeah, thank you, Jacob. 0 to infinity, those are the correct endpoints. I'd like to be really careful about the delimiters. You know, that's the word for like parentheses or brackets, the delimiters that we use here. So is 0 a part of the range or not? The suggestion from chat was that the range should be the interval 0 to infinity. And of course, we always use a parentheses on the infinity symbol, so we don't need to worry about that. Yeah, and Mark suggests that we update Jacob's recommendation to the bracketed 0 here, and that's correct. But who can help me out with an explanation as to why? Why not a parentheses here? So remember the difference between the paren and the bracket, right? This is like our activity from last time. The bracket means, perfect, Kendra. Yeah, the bracket means that this endpoint is included in the set. So is 0 a part of the range? In other words, is there a point on the graph whose y value is 0? The answer is yes, it's this one right here. Right here, the x value and y value are both 0. So if we wanted to use our highlighters and play that smooshing game again, remember we can smoosh the whole graph in like this. And when we do that, you can see that, yeah, 0 does get hit. And so my range would be everything bigger than or equal to 0. Right, my range is and 0 is indeed included there. Okay. Let's jump a little bit deeper into homework 6 and see if there aren't some more interesting problems here that we can look at. Where are we? We are this class is, oh yeah, we're good. We got you guys for 75. That's right. Okay, x and y intercepts. I'd like to look at something. Okay. Maybe I should show you how to graph one of these more complicated fellows before. Yeah, we're going to need to do this too. Okay. Any questions on this fellow before I move on to something a little bit more complicated? So next I'm going to show you how to graph a more complicated absolute value function, and then we're going to talk about equations and inequalities. Any questions on how we got this graph, how we got the domain, how we got the range? Before we move away, there were two other little questions here. Where is this function increasing? And where is this function decreasing? And before we try to answer this, I want to make a comment on this. Answers about increasing and decreasing, these are always intervals of x values. And it's the x values part that people tend to make mistakes on. So if I ask you, where is this function increasing? You should always give me an interval of x values for your answers. I don't want points. I don't want ordered pairs. If I ask you, where is a function increasing or decreasing? You always need to give me some subset of the domain, right? Always intervals of x values. Now, what does it mean to be increasing? What does it mean to be decreasing? The trick is to imagine yourself as a little dude, and I do this with my calculus classes. Imagine you're a little dude walking along the graph from left to right. If you're going downhill as you walk from left to right, then you're decreasing. And if you're going uphill as you walk from left to right, then you are increasing. So here, I would say we are decreasing everywhere over here. Because as I walk along this graph from left to right, I'm going downhill everywhere over here. So on this part of the domain, we are decreasing because this is where we're going downhill. So what is this blue interval here? This blue interval here on which we are decreasing. What is that interval? Remember, you can hold space to talk or type in chat. Yeah, good. Thank you, Sophia. Exactly. Negative infinity up to 0. And you got the delimiters exactly correct. Negative infinity up to 0. Why do we not include 0 in the interval on which this function is decreasing? Why should I use an open parentheses here? I'm sorry, I wrote this under increasing, didn't I? I'm so sorry. We're doing decreasing first. Negative infinity up to 0. Why do we use an open parentheses here instead of a square bracket? Why do we not include 0 in that set? Why is it not fair to say we're decreasing at this point right here? Yeah, 0 is a point where we're turning around. We're going from decreasing to increasing. So we're neither increasing nor decreasing at this point. In fact, you'll see that these intervals of x values that you use to answer your increasing and decreasing things, they're always going to be open. Because at this point, and at any point where you turn around and go from increasing to decreasing, you're neither increasing nor decreasing. It's like as you walk over the top of a hill, right? As you're walking up, 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 your height is increasing. And as you go over the hill and start walking down, 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 your height is decreasing. But for that brief second, right at the top of the hill, you take one step there for a second where you're not going up or down. It's a level step as you turn around. So the very top of the hill or the very bottom of the valley, you're not increasing or decreasing there. So this end point, this bottom of the valley here, is not a point where you would be going downhill or uphill. You would be doing neither. So you're not decreasing at 0. And for that same reason, we would use an open interval here and say you're not increasing at 0 either. You're doing neither of those things. Okay. I want to say one more time that when you're talking about increasing and decreasing, you always need to give me intervals of x values. This is very, very important. Next time, I'll leave this here for just a second. Anybody who's still writing anything, give about 15, 20 seconds here, and then we're going to graph a more complicated absolute value function, and we're going to talk about solving equations. Okay. So Matthew, I'm going to answer that publicly if that's okay. He's asking, how do we know when to use brackets? The sort of high-level strategic answer there is you use a bracket when you want to include that number in the set. For example, 0 is in the range here, right? Because there is a point on the graph whose y value is 0. So I do want to include 0 in the set of the range. But when it comes to increasing and decreasing, the points where we turn around and go from increasing to decreasing, or like this point where we go from decreasing to increasing, at those turning points, they're called, we're neither increasing nor decreasing. So everywhere to the left of 0, we're decreasing. Everywhere to the right of 0, we're increasing. But at 0 itself, we're doing neither of those things. So we wouldn't include 0 in either of these. And that's always going to be the case when we talk about increasing and decreasing, that turning points aren't included. So in general, we will use brackets when we want to include that number in the set. And the factors we will use to decide whether a number is or is not in the set will depend on the question we're trying to answer. For increasing and decreasing, you have to ask, are we going downhill at that point? Are we going uphill at that point? And if the answer to that question is yes, then you would use a bracket or you would include that number in the set. If the answer to that question is no, then you would use a parentheses to exclude the number from that set. And there are plenty of times when we will want to include numbers in a set, but when it comes to the specific question of increasing and decreasing, turning points will not be numbers where we want to include in the set, because at the x value 0 here, where I turn around from decreasing to increasing, I'm not going downhill at this point. And I'm also not going uphill at this point. I am briefly, just for that instant, doing neither. So 0 isn't included in the increasing or decreasing. These are really good questions. I'm really glad that you guys are interacting. It makes me feel much better about these online classes to have a little bit of interaction. So please, and thank you for typing and asking questions. It means a lot. I'm going to move on now. I'm going to show you how to graph a slightly more complicated absolute value function. And then we're going to look at a related equation and inequality. Let's do the absolute value of x minus 2 all minus 3, like this guy. Now again, if I don't have any other information to go on, I should make a table. This time, rather than calling this thing f of x, I'm calling it y, but we know that those really mean the same thing. F of x is just a function notation that helps us imagine this as an input and output thing. But just like I made a table x and f of x, here I'm going to make a table x and y. And I'll start using the same x values I used before. But we may see that we can't quite figure out what's going on from those, so I might need to use a few more x values. If I feed -2 into this expression for x, -2 minus 2 already here, absolute value of -2 minus 2 minus 3, that's the absolute value of -4 minus 3, which is 4 minus 3, which is 1. This is a minus. So -2 comma 1 is on my graph. If I feed this equation -1 as an input, then I get the absolute value of -1 minus 2 minus 3. Now -1 minus 2, that's -3. So this is the absolute value of -3 minus 3. The absolute value of -3 is +3. So this is 3 minus 3, which is 0. And I'll do this for the other inputs. Absolute value of 0 minus 2 minus 3. That's the absolute value of -2 minus 3, which is 2 minus 3, which is -1. The absolute value of 1 minus 2 minus 3. So I'm feeding x equals 1 into this now. 1 minus 2 is -1, so this is the absolute value of -1 minus 3. The absolute value of -1 is 1, so that's 1 minus 3, which is -2. And when I get to 2 here, I'll have the absolute value of 2 minus 2 minus 3, which is the absolute value of 0 minus 3, which is 0 minus 3, which is -3. So I'm going to take what I have so far and start to draw a graph. See what we get. Okay, I have -2 comma 1. So let me mark off my x values so far. I've got those and 1, -1, -2, -3 for y values. So the first row of my table tells me -2 comma 1 is on the graph. All right, here is -2 comma 1. Second row of my table tells me -1 comma 0 is on my graph. Here's -1 comma 0. The third row of my table tells me 0 comma -1 is on my graph. Here's that point. Then I have 1 comma -2. That's this point. And 2 comma -3. That's this point. Now what I'm not seeing here, I know that absolute value graphs should have this V shape, but so far I can't even tell where the V is. So I should give some more inputs, right? And you'll see this happen a lot. Sometimes you'll start to make a table and you'll realize after sketching those points, I really can't tell what this graph looks like yet. So let's add some more points in. Let's go 2, 3, 4, and 5. If I plug 3 into that equation, then I get the absolute value of 3 minus 2 minus 3, which is the absolute value of 1 minus 3, which is 1 minus 3, which is -2. If I feed in 4, I'll have the absolute value of 4 minus 2 minus 3, 4 minus 2 is 2, so that's the absolute value of 2 minus 3. And that's 2 minus 3, which is negative 1. And if I feed this thing 5, I'll get the absolute value of 5 minus 2 minus 3. 5 minus 2 is 3, so that's the absolute value of 3 minus 3. And the absolute value of 3 is 3, so this is 3 minus 3, which is 0. So now I have some more points. I can add tick marks for 3, 4, and 5 to my graph here, and add these ordered pairs. So when x is 3, y is negative 2. So okay, I've got 3 comma negative 2. When x is 4, y is negative 1. So I've got 4 comma negative 1. And when x is 5, y is 0. So I've got 5 comma 0. Now I can see my shape, right? Now I can see this graph. So with a little more information, making my table a little bigger, use these nice fat points here. Now I can actually see the shape of this graph. So this is another V-shaped graph, and all of the absolute value graphs will be this V-shaped graph. Here, the pointy bit is at the coordinates 2 comma negative 3. I'm decreasing everywhere from negative infinity up to 2. I'm increasing from 2 to infinity. Let me go ahead and answer those questions here. So you see, I'd be walking downhill along this graph everywhere over here. So we're decreasing. Imagine walking left to right. I'm going downhill, 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 downhill until I get to here, where the x value is 2. So I would say we're decreasing from negative infinity up to 2. And again, at this point, I'm neither decreasing nor increasing. So I don't include 2. And then I'd be going uphill everywhere to the right of there, yeah? So I'll be increasing everywhere from 2 all the way off to infinity. And remember, we're always thinking of these as intervals of x values. So the interval of x values on which I'm decreasing is this one. And the interval of x values on which I'm increasing is this one. It's the swooshing game again. Once you've identified the part of the graph that is decreasing and the part of the graph that is increasing, you have to smoosh the graph, just that part, onto the x-axis. So here's the part of the graph that's decreasing. And if I smoosh that onto the x-axis, I get negative infinity to 2. Here's the part of the graph that is increasing. I don't think any of us would have a hard time finding that. And if I smoosh just that part of the graph onto the x-axis, I get the open interval from 2 to infinity. My domain is again all real numbers, or negative infinity to infinity. What's my range here? What do I get if I smoosh this whole graph onto the y-axis?
Would it be -3 and then to like infinity?
Yeah, I think both Kendra and Logan have the right sort of ideas here, but we need to be a little bit more careful. Imagine I take this whole graph and I smoosh it onto the y-axis. Well, then this point is going to get smooshed to here, right? So my range actually starts down here. And if I smoosh this whole graph onto the y-axis, everything from here and up gets hit. So my range really looks like this. This is my range. So the range would be the close bracket -3 to infinity, right? Because the smallest y value on the graph right here is -3. And we do hit that y value. Okay. Questions about how we got this graph or how we answered these questions of increasing, decreasing, domain, and range?
For the increasing and decreasing, wouldn't it be 3 instead of 2?
Well, remember we have to use intervals of x values. So what is the x value where
Oh,
we turn around?
that's right. Sorry, never mind.
Okay,
Never mind.
no, you're good. Yep. So it's a common sticking point, right? And that's why I made that note on the previous page, is that we're really tempted to give answers in terms of y values. But for increasing and decreasing, it always needs to be intervals of x values. So we're decreasing everywhere along this x interval, which is -infinity up to 2. And we're increasing everywhere along this x interval, which is 2 to infinity. So I'm really glad you mentioned that, because this is something that our brains naturally want to do, but we need to fight a little bit. Okay, I have a bonus question here, a little extra something. Now that we have a really nice graph of this function, it would make sense to try and solve graphically the equation. So I'm going to cover this up. Solve using the graph the equation absolute value of x minus 2 minus 3 equals 0. All right, remember this is the graph, y equals abs x minus 2 minus 3. Okay. So can we use this graph to solve that equation? Well, compare this equation to this expression. I'm asking, where is this thing equal to 0, right? Absolute value of x minus 2 minus 3. Absolute value of x minus 2 minus 3 equals 0. So I'm asking, where is the y value, right? Because this thing is equal to y. I'm asking, where is y equal to 0? Yeah, Mark is correct here. This is when x is equal to -1, and also when x is equal to 5. So in other words, we're asking here, where along the graph is y equal to 0? And a neat trick in mathematics, the word where, anytime you find yourself looking at a graph and asking where is something happening, your answer is always going to be an x value. So where always means for what input or for what x value. So for what input, for what x value is y equal to 0. Well, I look along this graph, where are the y values along the purple graph equal to 0? Right here and right here. This is the point -1, 0. And over here, this is the point 5, 0. And those are the 2 points along this graph where the y values are equal to 0. So we get from the graph that the solutions to this equation are x equals -1 and x equals 5. What if I didn't have the graph? Is there a way I could solve this without the graph? The answer again is yes here. And the last thing I'm going to show you is sort of how to set up absolute value equations. So I'm going to solve this same equation, solve without graphing the equation absolute value of x minus 2 minus 3 equals 0. Are you ready for this? Here's the trick. Anytime you want to solve an absolute value equation, first, isolate the absolute value part. So here, that would mean I just have to add the 3 over. No, I've got absolute value of x minus 2 minus 3 equals 0. This is equivalent. I can add 3 to both sides to saying the absolute value of x minus 2 is equal to 3. Now you have to think about what the absolute value function does. I call this next step unpacking the absolute value. So what sort of numbers have absolute value equal to 3? Take a second and think about that. There's 2 numbers out there in the universe where I can take their absolute value and I get 3 out as the result. What are those 2 numbers?
3 and -3.
Beautiful. So unpacking the absolute value looks like this. That means the inside of the absolute value can be equal to 3, or the inside of the absolute value can be equal to -3. Did everybody hear Sophie's answer? We asked, what sort of numbers have absolute value equal to 3? And the answer there is, well, 3 has absolute value 3, and -3 has absolute value 3. So if you have the absolute value of some shit is equal to 3, one of 2 things must be true. Either the thing inside the absolute value is equal to 3 itself, or the thing inside the absolute value is equal to -3. This works in general. If you have the absolute value of some shit equals a constant, that is logically equivalent to saying the stuff inside the absolute value is equal to that constant, or the stuff inside that absolute value is equal to the negative of that constant. So this example, this is how things always work. No matter what variable stuff you have in here, and no matter what constant you have here, absolute value of some shit equals a constant is always equivalent to the shit equals that constant, or the shit equals the negative of that constant. Now here I can add 2 to both sides. 3 plus 2 is 5. Here I can add 2 to both sides. -3 plus 2, that's -1. And I get my 2 solutions. X equals 5, x equals -1. So that's it. Right, after you unpack the absolute values, now you solve the resulting equation. The last thing we need to talk about here today, and I am going to push the regression stuff to next week, we need to talk about absolute value inequalities. And unfortunately, we don't have a lot of time left, but there's an unpacking rule, just like the unpacking rule I shared for the equations. So in parting here, let me show you how to unpack absolute value inequalities. Inequalities. If you have the absolute value of some shit is less than some constant, this unpacks as the negative version of that constant is less than that shit is less than the positive version of that constant. And then you would solve this. Similarly, if you have the absolute value of some shit is less than or equal to a constant, the exact same rule works. Negative version of that constant is less than or equal to that shit, less than or equal to the positive version of that constant. And it's worth noting, absolute values are never negative. So in these examples, the constant here needs to be positive. So inequalities like absolute value of some shit is less than -3 have no solutions. Because there's nothing that you can take the absolute value of to get something smaller than -3. Because if you're smaller than -3, you're negative. The other unpacking rule for absolute value inequalities, if you have some shit is greater than some constant, this unpacks as either the shit is bigger than the positive version of that constant, or that shit is smaller than the negative version of that constant. And similarly, if this is a greater than or equal to, these will unpack as that shit is greater than or equal to that constant, or that shit is less than or equal to the negative of that constant. So these are your unpacking rules. These are for less than inequalities. These are for greater than inequalities. Before I let you go, let me tell you what I'm going to do with your homework, because we haven't gotten to talk about everything we need to. Been a little bit short on time. So homework 4, this due date's not going to change. This is due next Tuesday. Quiz 1 and homework 3, remember these are also due next Tuesday. I extended those to next Tuesday for you guys. Homework 5 and quiz 2, I'm going to extend. Let's just say homeworks 5, 6, and quiz 2. We'll extend all of these, all right? So right now, those are set to be due next Tuesday, the 19th. I'm going to push those back 1 week to the 26th. And we're going to try to work quickly through this stuff. The linear models and regression thing, this is not a hard section, but it requires good use of the calculator, and I hate trying to do this shit like this because you can't see the screen. So I got to talk to SFIT and get my emulator working correctly, and we'll do that. So make sure you finish everything up through homework 4 by next Tuesday, all right? You got to have all this done by next Tuesday. Homeworks 5, 6, and quiz 2, these are open. They will remain open, and I'll extend them another week so we can get in there and talk a little bit more detail about these things. I don't want you guys to feel stressed. I want you to take your time and really understand this. If you do get stuck on anything, if you're having trouble with anything, please come by an office hour. Remember, you can get to the office hours through Canvas. Just go to the home page for our course in Canvas. Monday, Wednesday, and Friday, 1 to 2, you can click here. Tuesday and Thursday from 11 to 12, you can click here. This is where I'll be going next. And if you can't meet during these times, please reach out to me. I have 5 other hours through the week that I set aside for office hour appointments. So don't feel bad about asking for an appointment. I purposefully leave 5 hours out of my schedule so that I can do appointment office hours. So please, if you can't come to these, but you want to talk to me, send me a Canvas message. We'll schedule a different one. All right? Any questions before we get going?
Can you go back to the notes for just 1 second?
Sure, of course.
Thank you.
Yeah, if you want to hang around, since the next thing is an office hour, I wouldn't mind doing an example of one of these. Would you guys like to see an example here? I know we're going over class time. I'll leave it up to you. Yay or nay? Well, I know you guys have other obligations. I don't think it would be fair for me to lecture something here if somebody had to leave. So rather than doing an example as a part of class right now, if you want to see an example early, I will do an example of these next Tuesday in class. But if you want to see one early, you want to talk a little bit more about this, come meet me in my office hour. I'll be there in 10 minutes. Is there anything else from the notes that you guys wanted to see? You need me to go back a page, anything like that? Okay. I am going to get running. This lecture will be up on YouTube in about 30 minutes. I hope you guys have a lovely rest of your day. And again, please don't hesitate to come see me in office hours if you want to talk about math. Take care.
Thank you.
Thank you.
Of course.